Welcome to the Problems channel, Season 2, Episode 27, the episode which I titled Finite Integer Power Sums Revisited, because in this episode we will discuss a slightly improved algorithm for constructing alternative expressions for the integer power sums, whose structure is shown in the upper right corner of your screen. Before we do that, however, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the home page of this channel and in the channel's trailer section, find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In our new challenge, the mathematical problem S2E27, we were asked to inhale all the information that we have covered during the solution of the previous problem, S2E28, which we covered in the previous episode, the Season 2 Episode 26, and to construct an algorithm that is less computationally intensive than the algorithm that we described in the Season 2 Episode 28 for the evaluation of finite integer power sums, whose structure is shown in the upper right corner of your screen. Before we deep dive into the underlying mathematics, however, I would like to let our viewers who may be interested in it to visit the corner of this channel called Posts, which is pointed at with red arrows in the upcoming image. And browse through that section, because I do my best in order to let you guys know which new episodes will be coming on this channel in the near future, precisely in that section of our channel. In the previous episode, the Season 2 Episode 26, we described one algorithm that can be used in order to obtain an alternative expression for the finite integer power sums whose structure is shown in the upper right corner of your screen in a straightforward and mechanical way. And that algorithm amounted to expanding the scope of both the number of terms in the corresponding and underlying sum from n to n plus 1 and the magnitude of the corresponding power from p to p plus 1. Then, according to that algorithm, we had to expand binomially the resultant n plus 1 raised to the power p plus 1 expression, iterate that binomial expansion n minus 1 times by replacing n with n minus 1 in each consequent iteration, sum all the resultant equations, witness a lot of favorable cancellations, arrive at an equation that was linear in the sum sought after, and as a final step, we were also asked to substitute all the previous sums in that equation with their own corresponding alternative expressions. And that algorithm basically tells us that in order to compute or evaluate the finite integer power sum in the shape Sp, where each and every summand is raised to one and the same fixed and given ahead of time power p, we had to consecutively evaluate all the previous sums, and that amounted to quite a bit of work. However, at the end of the previous episode, we also collected a reasonable amount of evidence that showed that each and every such sum, for example, the sum shown over here, here, and here, can be represented as a function of n as a polynomial of the degree that is precisely by 1 larger than the fixed and given ahead of time power p, to which each and every summand of the corresponding sum is raised. And at the end of that episode, we ask you guys to inhale all that information and to come up with an algorithm that is less computationally intensive, but it still allows us to evaluate the underlying integer power sums also in a mechanical and perhaps a straightforward way. And indeed, in the theory of polynomials, there exists a theorem which, again, depending on the level of the machinery that is used to prove it, it could be relatively short, but it uses higher level machinery. With the lower level machinery, it may be a little bit lengthy, but it's not that complicated. But overall, basically, this theorem confirms our assumptions that we generated at the end of the previous episode. That is, according to that theorem, the sum of the finite sum of integer powers where the power p is fixed and given ahead of time as a function of n is indeed a polynomial of degree p plus 1, precisely p plus 1. Armed with that theorem, and again, I just want to make sure that everyone understands that that process of constructing this algorithm, trying and failing and fishing out this more or less standard unit of mathematical knowledge from our collective web of mathematical knowledge is, or exactly what constitutes doing mathematics or a dress rehearsal of grown-up mathematics. Everything that follows animating this algorithm or animating this templatized approach to evaluating the sums is really not mathematics, or perhaps lesser mathematics. In any case, by trying and failing several times and by using the theorem shown over here, we can put together the following algorithm that is less computationally intensive. It is still quite mechanical, and it still allows us to take any finite integer power sum in the shape shown over here and construct an alternative expression for that sum. This is also a four-step algorithm, and according to the first step of that algorithm, we should take our finite integer power sum and record it in two different but equivalent ways. First, we record it as the original sum or as an explicit sum, and then we record it according to this theorem as a polynomial of degree p plus 1. That's step number one. In the step number two, we iterate these expressions that we obtained in step number one by replacing n with n plus 1. And just to make sure that we all understand it, this step over here this time constitutes the manifestation of the scope expansion problem solving approach whose mechanics we're studying right now. So in other words, in the first step, we will obtain two expressions. In the second step, we will also obtain two expressions, and thus overall we will have four expressions to deal with. In the step number three, we construct two differences between the shape of the given finite integer power sums that are written down explicitly and the difference between the two corresponding expressions for the polynomials at hand. And in order to record the finite integer power sum as a polynomial, we'll use certain coefficients. And the final step of this algorithm, step number 4, calls for equating these differences, juxtaposing one difference against the other, and then using this result as the fodder for the recovery of the underlying coefficients of this polynomial, and voila, we have an alternative expression for a given finite integer power sum. Now that we know the description of this new and computationally less intensive algorithm, let us see how it will work, for example, for the sums S1 shown over here and S2 shown over here, and it will work in exactly the same way for all the consequent sums. But we will begin our short algorithmic journey with the sum S1. As usual, the way these things work in hard sciences, mathematics, theoretical physics, and computer science, if you do not know about something, then that something seems to be very scary, very difficult, and very important. But the moment you learn and understand how that something works, then all of a sudden, and as if by magic, it stops being scary, it stops being difficult, and it's not that important all of a sudden and anymore. As such, in the previous segment, we described a less computationally intensive algorithm for evaluating the finite integer power sums. And in this segment, we want to apply that algorithm to the process of recovery of an alternative expression for the finite integer power sum S1 shown over here. What was the first step of that algorithm? Well, the first step of that algorithm was to write down our sum in two different but equivalent ways. One way will be an explicit rendering of the sum, and the other way will be the rendering of that sum as a polynomial of degree which 1 plus 1, 2 as a polynomial of degree 2. So here we write down the sum as 1 plus 2 plus 3 plus and so on plus n. And what is that? According to our theorem, this will be an squared plus bn plus c, where a, b, and c are constant, unknown to us yet real numbers, and we will recover the magnitudes or the values of these constants precisely by following the algorithm that we described in the previous segment. This string of symbols constitutes what? It constitutes the first step of our algorithm. What is the second step of our improved and less computationally intensive algorithm? The second step of our algorithm says that we need to take both expressions that we generated in the step number 1 and iterate them via the n plus, replacing n with n plus 1 in each iteration. As such, we write down the following: S1 of n plus 1, because now n becomes n plus 1. And here, what will we have? Essentially, this iteration tells us that instead of summing our consecutive whole positive numbers k from 1 to n, we're running the sum from n to n plus 1. And this is precisely, to be sure, the place where the scope expansion problem solving approach, which we're studying now, manifests itself. Usually we think, or intuitively, we would like to make our problems narrower, smaller, and simpler in some sense. But according to the scope expansion problem solving approach, sometimes in mathematics, theoretical physics, and computer science, it is advantageous to make our problems seemingly wider, larger, and more complicated. However, that is not the case, precisely because in certain situations, in certain cases, when we make when we expand the local material of the problem at hand, we actually gain a certain competitive advantage. So here our sum will run which way? It will run plus n plus what? Plus one more term, n plus 1. And that is equal to what? We iterate this expression by replacing n with n plus 1, and we'll obtain a n plus 1 squared plus b n plus 1 plus what? Plus c. There is no more material that varies. That game over. The constant unknown to us yet number c just goes into the next expression as is. So that constitutes the end of the step number 2 of our improved algorithm. What is the step number 3 of our algorithm? The step number 3 of our algorithm prescribes that we construct the difference between the iterated expressions and the original ones. So here, let's say we'll write it as a delta. What? From the sum s n plus 1 written out or spelled out explicitly, we subtract the sum sn. So what will be the result of this difference? Precisely, the only term that will survive this difference will be n plus 1. So we write down n plus 1. And what is the difference between the iterated polynomial and the original polynomial? Well, this is nothing but the trivial middle school arithmetic, but let us carry it out together. So what will we have on the right hand side? An squared plus 2an plus a. Everyone understands where this string of symbols came from. We spelled out n plus 1 squared and multiplied it through by a. What is this guy? Well, this is plus bn plus b plus c minus, what are we subtracting from this polynomial? The original one, minus an squared minus bn minus c. Everyone understands where this material came from. Very well. So now what do? We see what can be canceled because we have a difference of two related things. An squared with the plus sign, an squared with the minus sign, gone. What else? Bn with the plus sign and bn with the minus sign, gone. What else? Obviously, the material that does not vary at all with respect to n will be gone too. Plus c, minus c, gone, gone. Anything else that survives this subtraction? No, not really. This is it. So now what do we have? We have, let's write it down maybe somewhat officially, delta as S1 of n plus 1 minus S1 of n will be what? N plus 1, n plus 1, and what is it on the other side of the equal sign? We'll have the sum on 2 times a times n, 2 times a times n, this is the product sign, plus what? Plus a and b and nothing else, plus a plus b. Now, this expression over here constitutes the end or the goal of the step number 3 of our computationally less intensive algorithm. And how many steps are left in this algorithm? Only one, the step number 4. So now I will take a short break and erase this material that you see over here. And we will fight it out in the last and the final step number 4 with this one, but you guys can go ahead. You don't have to wait for me. With your pen and paper, you can finish the computation. What is the tactical idea of this step? The tactical idea is similar to what we do with complex numbers, for example. With complex numbers, we obtain two different but equivalent equations, and then we equate what? The real part to real part, and then imaginary part to imaginary part across the equal signs. Here, we don't have complex numbers. All numbers seems to be real, but what do we do here? Well, we have the material in n on the left-hand side of the equal sign, and we have a certain material in n on the right-hand side of the equal sign. And thus, the tactical idea here is to equate the coefficients that are attached to the same, exactly the same or equivalent powers of n. How many powers of n do we have in this equation? Precisely, we have exactly 2 powers, the first power and the 0th power. So while I'll be erasing this with your pen and paper, you can work out what? 2a will be what? 1, and this one will be what? A plus b. And you take it from there. But for now, I'll take a short break and erase this material and prepare it for the next segment. Very good. Now that we all understand where did this expression come from, we take it home. In the previous segment, we showed that the difference n plus 1 is none other than what? 2 times a times n plus a plus b. And how do we massage, or how do we exploit, how we extract actionable mathematics from this expression? Well, it's the same idea, as I mentioned in the previous segment, as we exercise with complex numbers. With complex numbers, we construct 2 different expressions that are equivalent, and then across the equal sign, we equate the real parts to real parts and imaginary parts to imaginary parts. Here, we don't have real numbers. We don't have complex numbers. All the numbers seems to be real. But we have the material that varies over n. And now the tactical idea is to equate the coefficients that are attached to exactly the same powers of n. How many powers of n do we have in this expression? Exactly 2, 1, and 0. So we roll through our equation, if you will, and to each power of n, we examine for each power of n which coefficients are attached to it. So here to the power of n, that is 1, on this side of the equal sign and this side of the equal sign, what coefficients do we have attached? Here is basically 1 times. So first we write 1 is equal to 2a. And now we have 1. Here we can say 1 times what? N to the 0th power. And here is the same thing, times n to the 0th power. So what do we say? 1 is equal to a plus b. Normally, we can treat it as a system of simultaneous equations, but here we can actually see what's going on right away. From the top equation, it follows what? That a is equal to 1/2. That is straightforward. And if a is 1/2, then what must be b in order to be added to 1/2 and add and obtain 1? No computations needed. From here, we instantly get that b is equal to 1/2 as well. So what does that mean? We go back to our previous theorem, which states that each and every finite integer power sums that has the shape is a polynomial in n of degree precisely p plus 1. So let's write it down over here. Our sum Sn S1 of n, that is the sum of k raised to the first power, where k varies between 1 and n, is what? Is the polynomial in n of the second degree. So it will be what? 1/2 times n squared plus 1/2 n plus c. Now the question arises, what is c? Well, let's do this. In order to recover the value of the constant real number c, what experiment can we do? Well, we can cache in certain numbers. Let's say, what is S1 of 1? So when n is 1 and we have only 1, so let's do this. S1 of 1 is equal to 1, and this is equal to what? 1/2 times 1 squared plus 1/2 times 1 plus c. So what does that tell us? What does this experiment tell us? Well, 1/2 plus 1/2 is 1. So essentially we have 1 equal to 1 plus c. What does it imply? It implies that c is a big fat 0. So now we know the answer to our problem, to the question that we posed earlier. This is precisely the answer, the polynomial, a polynomial in n of degree 2. The coefficients of this polynomial have been recovered. Bam, we know the exact shape of the alternative expression for this finite integer power sum. And again, we can shuffle symbols all you want. There is a deep, significant, and meaningful mathematics behind leaving this formula exactly like that, and I'll talk about it in a few minutes later. But for now, for those who are used to our middle school format of this formula, we can collect everything under one denominator, which is 2, factor out n, and we have familiar to us n times n plus 1, the number of handshake, and so on, formula for the finite integer power sum S1. Now that we understood how this improved, less computationally intensive algorithm works for the finite integer power sum S1, let us apply it. Let us apply that algorithm to the process of recovering the shape of an alternative expression for the finite integer power sum S2. Now that we understand how the simplified and less computationally intensive algorithm work when it is applied to the recovery of the alternative expression of the finite integer power sum S1. In this segment, we'll carry out the equivalent computation for the sum S2. But again, fundamentally and essentially what that means when we say the words an algorithm, that all the steps that are carried out according to that algorithm are the same. They're mechanical. They do not really change. The only thing that changes is a little bit of a local substance and a little bit of the local material. But the gist, the technical essence of the steps that we carry out does not change. As such, when we apply our less computationally intensive algorithm to the sum S2, what do we have? Step number one, write down our sum, spell it out explicitly. 1 squared plus 2 squared plus so on plus n squared is, according to the theorem that we mentioned at the beginning of this episode, is what? Is a polynomial in n of degree what? P is 2, p plus 1 is 2 plus 1 is 3, so this is the polynomial of the third degree. How do we write it down? A times n to the third plus b times n to the second power plus c times n to the first plus d, where a, b, c, and d are constant, unknown to us, yet real numbers, whose values are to be recovered as we follow the steps of our algorithm. Step 1. Step 2. Iterate both expressions obtained in step 1 by replacing n with n minus 1. So effectively, S2 n plus 1 is 1 squared plus 2 squared plus so on plus n squared plus what? N plus 1 squared. Because again, essentially with this iteration, we're saying what? We're saying that our sum is computed not from 1 to n, but from 1 to n plus 1. So again, seemingly, we expand the problem over here. Instead of making it smaller, simpler, and easier to handle, we're making it wider, larger, and seemingly more complicated as per the expansion, scope expansion problem solving approach. But as we already saw in the previous segment, by doing so, sometimes we actually gain a competitive advantage. So here, the polynomial in the iterated form will be what? n plus 1 to the third plus b, n plus 1 to the second power plus c, n plus 1 plus d, or the material that does not vary. Bam, step number 2. Step number 3, construct the difference, the delta between S2 n plus 1 minus S2 of n. What do we have? Well, from this expression, we subtract all this material. Everything is gone nicely, cancels out nicely. What is left? N plus 1 squared, spell it out. N squared plus 2n plus 1 is equal to what? What follows here is again a straightforward mechanical, in some sense quite boring, finite computation with all the life, with all the joy of improvisation and creativity and ingenuity sucked out of it. If you know how to handle it, fast forward. If not, stick around. So here, what do we have? an cubed plus 3an squared plus 3an plus a plus bn squared plus 2bn plus, let us see, we'll keep it over here, plus 2bn plus b plus cn plus 1 plus d. This should be understood by everyone. There is no secrets over here. We simply took the binomial expansion of n plus 1 to the third power. We took the binomial expansion of n plus 1 to the first power. This requires zero algorithmic or computational effort. We wrote down all these symbols. And now what do we do from the iterated polynomial? We subtract the original one. So we subtract, what is it? an cubed minus bn squared minus cn minus d equal to, let's see if we can swing this result together. Where is my red chalk? So here, what do we have? We have, look at this, an to the third with the plus sign, an to the third with the minus sign. What else do we have? What are the good candidates for cancellation? Well, bn squared minus bn squared. What else do we have? We also have d and d over here. Anything else? Yes, plus cn minus Cn. Anything else? It doesn't look like it. So what do we have? Let's write down carefully the powers of n in the decreasing order so we can correlate the coefficients that are attached to n that is raised to 1 in the same power. So here we will have 3a n squared plus, what do we have? 4n raised to the first power. 3a, 2b. Anything else that varies in n? Nothing. So plus 3a plus, what is this? 2b n. 3a plus 2 times b times n. And what else do we have? We have a, we have b, and we have, where is Cn plus c, and we have c over here. Instead of c, I wrote down 1. So, and we have c. So plus a plus b plus c. And what is this equal to? This is this guy. So let's write it down. N squared plus 2n plus 1. Look at this wonderful result. This is the end of the step number 3. We all understand where did this material come from. N squared plus 2n plus 1 is 3a n squared plus 3 times a plus 2 times b times n plus a plus b plus c. And now we all understand by analogy with what we did in the previous segment. In the next segment, you guys can go ahead. You don't have to wait for me. I will take a short break to erase the material on the board over here to prepare it for the next segment, but you will all understand what will happen in the next segment a few seconds later. We will equate the coefficients attached to n squared on both sides of the equal sign. So we will write what? 1 is equal to what? 3a. 2 is equal to what? 3a plus 2b. And 1 is equal to what? A plus b plus c. And we'll take it from there. We'll have, in theory, we'll have 3 equations, 3 unknowns, and hopefully we will recover the values of all these coefficients. Excellent. In the previous segment, by constructing two differences, the difference between the iterated sum S2 and its original form, and the difference between the iterated polynomial representation of that sum and the original polynomial, we discovered that that difference yields the following relationship between the coefficients a, b, and c. This time the coefficient d disappeared, and the material on the left-hand side of the equal sign. And now we execute the same maneuver that we executed when we worked with the sum S1, which is what? We count the number of powers of n on the left-hand side of our equal sign and on the right-hand side of the equal sign. How many such powers do we have on the left-hand side? 1, the second power, that's 1, the first power, that's 2, and the 0th power, that's 3. Likewise, we have 3 powers of n on the right-hand side of the equal sign. 2, 1, and 0. And what do we do now? Now we equate the coefficients that are attached to like powers of n on either side of the equal sign. By doing that, what do we see? 1 attached to n squared on the left-hand side of the equal sign. 3a as a coefficient attached to the n squared on the right-hand side of the equal sign. Hence, we claim that 1 is equal to 3a. Next, 2 as a coefficient attached to n raised to the first power on the left-hand side of the equal sign. And what? 3a plus 2b is attached to n raised to the first power on the right-hand side of the equal sign. Hence, we claim that 2 is equal to 3a plus 2b. Lastly, 1 is attached to n raised to the 0th power on the left-hand side of the equal sign, and the sum a plus b plus c is attached to n raised to the 0th power on the right-hand side of the equal sign. Hence, we claim that 1 is equal to a plus b plus c. Now we have a system of three equations with three unknowns. These are technically simultaneous equations, but from the first one, we instantly conclude what? A is 1/3. Beautiful. 3a taken from the first equation and injected over here means what? 1 plus 2b equals 2, which means that 2b equals to 1, which means that what? B is equal to 1/2. From here it follows that b is equal to 1/2. So now we massage the last equation shown over here. 1 is equal to what? 1/3 plus 1/2 plus c. 1/3 plus 1/2 is what? 5/6. So what number must be added to 5/6 in order to yield 1? 1/6. Consequently, from here we instantly recover c is equal to 1/6. So now it seems that our finite integer power sum S2 can be represented as a polynomial. In which way? S2 of n, that is a sum where k runs from 1 to n, where each k is squared, will be what? 1/3 of n cubed plus 1/2 of n squared plus 1/6 of n plus the coefficient d. So now we had three simultaneous equations, three variables. We recovered the values of all these variables, but now we still have one constant real number d left over. How do we recover its value? We execute the same maneuver. When the sum S2 is evaluated at n equals 1, then we have what? 1 squared equals to 1, and that is what? 1 cubed over 3 plus 1 squared over 2 plus 1 over 6 plus d. And what does that observation tell us? This observation tells us that 1/3 plus 1/2 plus 1/6 is 1. This is precisely 1. So now we have 1 is equal to 1 plus d, and this implies what? That the d is again a big fat 0. And now we don't really have to write it down over here. Again, there is a fairly deep and meaningful mathematics behind leaving this sum as shown over here. For example, if we take the first derivative of both sides with respect to n, what will happen over here? 3 and 3 cancel each other out, and we have what? N squared. 2 and 2 cancel each other out, and we have 1. Conversely, if we integrate the derivative, we will bump up the coefficients. N cubed 1/3, n squared 1/2, and so on. But many people are used to slightly different form of this relation, so of this formula. So what do we have? How can we massage it? Well, let's write it down. Let's write it down over here in this section of the board. Let's massage this guy. What do we see with n? N is present everywhere. So if we cancel out, if we factor out one copy of n, what will we have? We'll have n over 6. N over 6 will bring everything to one and the same common denominator, which is what? 6. So we will have 2n squared left with this copy of the square of n, 3n plus 3n left with this summand of n squared. Here the denominator is 6. We multiply by nothing, by 1, let's say, so we keep plus 1. And what do we do with this? How do we factor? You can solve your favorite quadratic equation, but we act in a mildly clever way. Here we represent 3n as the sum of what? 2n plus n. So if we rewrite 3n as 2n plus n, so what will we have? We will have, let's say, 2n squared plus 2n plus n plus 1. You see, this is n plus 1. If we factor out 2n, what we will have? 2n times n plus 1 plus n plus 1. So the rest of the manipulation is transparent. You already recognize n plus 1 is a common factor. We carry it out, and what do we have? We have the formula. Let me erase the, once you understand where did this manipulation come from, you can carry it out again. We basically decompose 3n into the sum 2n plus n, and the rest is straightforward middle school arithmetic. And thus, if I'll erase this manipulations, once we all understand where did it come from, then it is more than straightforward to see that the answer is what? N times n plus 1 times 2n plus 1 over 6. This is our S2 of n. This is our result. And the reason why we put together this mini series about this finite integer power sums that lasted for 2 episodes is to highlight the fact that this is just a tip of the iceberg. There is deeper and more meaningful, more interesting, more grown-up mathematics that hides behind that. In general, it is possible to construct a formula that shows the expression, an alternative expression for the finite integer power sum, and that formula will deal with basically in slightly disguised form the so-called Bernoulli numbers. And to highlight more of meaningful and deeper mathematics behind it, you can put this video on pause and take your time, take an hour, take a day, take a week, take a month, think about it on your own. But think about the following question. For example, let's take this sum over here, our sum of squares of first n consecutive positive whole numbers, and try to answer the following question. What is a possible fruitful geometric interpretation of these numbers and of that sum? While it is possible to put several geometric interpretations of the sum S2 shown over here, the sum of squares of first n consecutive positive whole numbers, one geometric interpretation of that sum that proved to be mathematically fruitful is associated with the name of the French mathematician shown over here, Eugene Ehrhart. He lived between the years 1906 and 2000. He was quite an interesting gentleman. Apparently, he received his high school diploma at the age of 22, and eventually he worked as a teacher of mathematics in various high schools apparently, and he defended his PhD thesis in mathematics when he was 60 years old. So one interpretation of the sum finite integer power sum shown over here as 2 sum of perfect squares of first n consecutive whole numbers is the following. If we expand our sum a little bit, again, is we represent it as the sum of n plus 1 terms, and we hone in on the value of n over here, then the terms of this sum can be represented as layers or planes in a pyramid which is square. The pyramid has a square base in the x, y, z space. And the way it works is as follows. The base of the pyramid will be square again. The coordinates of the lower, let's say, left corner of that square shown over here will be all 0, 0, 0, 0. Along the x-axis, the coordinate will be n, 0, 0 shown over here. Along the y-axis, the coordinate will be 0, n, 0 shown over here. The upper right corner, if we look down on that square base, will be what? Will be n, n, 0. This will be the coordinates of this point. And then this pyramid apparently has the vertex at the point that has these coordinates 0, 0, and so in general I skewed it a little bit, but if we are to look at the realistic pyramid, then it will go vertically up like this, and then we cut it with the square sections or square planes. So what that means is the following. If we name the plane Z that runs this way across the plane of our monitors, and we name this place n minus I, then there will be precisely I plus 1 squared points in that plane. For example, when I is equal to 3, and which is n, for example, here the case that represents the sum S2, 3 plus 1, then the number of points in that plane over here will be 3 plus 1 squared, 4 squared, or 16. And this is exactly what we see. 1, 2, 3, 4 points along the x-axis, 1, 2, 3, 4 points along the y-axis. 4 times 4 is 16. This is our zeroth plane, so to speak, that coincides with the x, o, y plane. And then as we climb up, we go through the numbers I equals to 2, 1, and 0. Consequently, 2, 1, and 0. At the top, we have evidently only 1 point. So this is our plane over here. And this is one interpretation again of the finite integer power sum S2. It is associated with the name of the French mathematician whose name is shown over here. And for example, one interesting question that we can ask in that regard is the following. If we execute the homothety of the space that is centered at the origin with a positive and let's say integral coefficient, then how many such unit or how many such nodes on the unit cube lattice of the space will be included in such a pyramid. What does a homothety of the space centered at the point O with the positive integral coefficient mean? The homothety of the space centered at the point O at the origin with a positive integral coefficient, for example, 2, means that along each axis, along the x-axis, along the y-axis, and along the z-axis, we execute one and the same stretching, so to speak, which increases every distance by, for example, 2 if the coefficient of homothety is 2. If the coefficient of homothety is 3, then we expand the space along all three axes, x, y, and z, at the same time, at the same rate, and we increase that distance, for example, unit distance by thrice, make it 3 times larger, and so on. And then our pyramid becomes larger, we are expanded. And the question is, if we look at our unit cube lattice that is constructed in space, how many such integral points, so to speak, will be included in such a pyramid? This is the question that was answered by this French gentleman whose name is shown over here. And I don't think that anyone in the room will object if we will say that to the questions that were covered in this episode a little bit and much deeper. We can even associate the term of the Ehrhart Theory, for example. So this is it for the mathematical problem S2M29, and we will address a new challenge next. In our next challenge, the mathematical problem S2M30, we're given a regular hexagon shown over here. 1, 2, 3, 4, 5, 6. Non-degenerate, interesting, substantial, and in that regular hexagon, a point is chosen at random. A point chosen at random inside the hexagon means that that point belongs strictly to the interior of that regular hexagon, not to any point on the boundary of the hexagon, but to the strict interior of the regular hexagon with the boundary of the regular hexagon excluded. So anywhere inside the hexagon, the point P shown over here in red, I did not mark it with P, it doesn't really matter, but such a point is chosen. Then that point is connected with every vertex of that regular hexagon as shown over here. Once that connection is done, then the area of our regular hexagon can be partitioned into two types of or two sets of triangles. The yellow triangle shown over here, the first yellow triangle, the second and the third yellow triangle, and the corresponding blue triangles. The blue triangle number 1, let's say, the blue triangle number 2, and the blue triangle number 3. The question in the mathematical problem S2M30 is the following. What is larger, what is smaller, or are they the same when it comes down to the areas, to the sum of areas of specific triangles of the same color? In other words, if we sum up the area of all the yellow triangles and then we sum up the areas of all the blue triangles, then we'll get two numbers, and the question is in what relationship these numbers are. Is the sum of areas of the yellow triangles larger than, equal to, or smaller than the sum of areas of the blue triangles? Obviously, by now, the indoctrinated audience on our channel knows that we're not really interested in the answer to this question. We're mostly interested in your story behind the answer that you will produce, whatever that answer is. And don't forget that right now we're studying the mechanics of the scope expansion problem-solving approach. This is a hint, which means that this specific problem can be solved if we look at it in a specific way that is suggested by the scope expansion problem-solving approach. This is it for this episode. Thank you very much for watching. Thank you for your time. Good luck. And I will see you in the next episode, in which I will present my solution of the problem S2M30.